Okay, this problem says a marble rolls off a tabletop 1 meter high. So 1 meter high is roughly the height of this table. And hits the floor at a point 3 meters away from the table's edge in the horizontal direction. How long is the marble in air? What is the speed of the marble when it leaves the table's edge? What is its speed when it hits the floor? Okay. So let me do a diagram first. I'm sorry? Okay, so when the marble leaves the table, what is the trajectory of the marble? It's a parabolic trajectory. That's half a parabola. It's part of a parabola. Okay. What is the only force acting on the marble? Gravity. Okay. So you get a parabolic trajectory when gravity is the only force acting on an object. All other forces are insignificant. Okay. So So when you set up these problems, that'll be your axis. That will be our default setting for the axis. What you want to do is write down your acceleration vector, and you want to do this in component form. So there's the acceleration vector, and you can see that that is 0 I minus gj. G is the acceleration due to gravity, which is 9.8 meters per second squared. And this is your initial velocity, which has an x component and 0 y component. It's traveling horizontally. Okay. So this is a problem in 2D. Okay. Now they tell you that the ball falls 3 meters and it's launched from a height of 1 meter. Okay. Now, you guys, if you think about this a bit, see, the higher you launch the ball from, what does that affect? That affects how long you're in flight. Okay. And you guys understand, if I shoot this marble fast, what will happen? It'll fall further, right? So, conversely, from the distance it fell, you should be able to calculate the speed. Okay? And the time of flight, how long is it's in air, depends on how high it's shot from. Okay? All right, so that's the kind of information you need to be aware of. Okay, so now let's look at, and also the x component of the motion of the marble is independent of the y component of the motion. Okay. So let's look at the x component of motion. Okay. So x minus x naught equal to v naught xt plus 1/2 ax t squared. All right, I'll do the initial problem slowly. Okay, what is the x component of the acceleration of the ball? 0. So this term is 0. We'll say we've set up our x, the origin of our axis there. What is the initial x component of the position? There is the x initial position when it leaves the table. This is 0. Okay. What is the initial x component of the velocity? We call that v naught. Okay. So x, x equal to v naught t. All right, this is 3 meters. Okay, so 3 equal to v naught t. Okay, now we want to find the horizontal component, how long was in air. Okay, so actually we'll find how long the marble was in air by looking at the y motion. Okay, so this is B, part of B. Okay, let's do A. Let's look at the y motion. Y minus y naught equal to V naught y t plus 1/2 ay t squared. All right, here is the initial y position, which is 1 meter. Here is the final y position, which is 0 meters. Initial y component of the velocity, which is 0. Ay is minus g. So 0 minus 1 equal to 0 plus 1/2 times minus g times t squared. Okay, so you can see that from the y component of the motion, we can get t. So t is 2. Okay, so meters per second square. And what you'll get is, so the second square comes to the top, and the square root of that is a second, okay? All right, so t works out to be 0.45 seconds. So the marble was in flight 0.45 seconds. Okay, and we can put that in there and then calculate the horizontal speed at which it left the table. Yep. So going back to B, so 3 meters equal to V naught times T. V naught equal to 3 meters divided by 0.45 seconds. And what is the speed when it hits the floor? So when it hits the floor, its velocity is tangent to the trajectory. Okay, so that's the final velocity. And what we want is the speed, its speed, so we want the magnitude of the velocity, okay, when it hits the floor. So for part C, Vx, that's the final velocity, is V naught x plus ax times t. Ax is 0, so the final x component of the velocity is equal to the x component of the initial x component of the velocity, which is 6.64 meters per second. Okay, this makes sense. The x component of the velocity is not changing because there's no acceleration in that direction. Okay. That velocity is constant. Vy, the y component of the velocity is changing because ay is non-zero. Okay, so this is equal to, and initial y component of the velocity was 0 minus gt, 0. So the final velocity is 6.64 I minus 4.41 J meters per second. What quadrant is this vector in? I'm sorry?
First quadrant?
Fourth quadrant. It's got a positive x component, negative y component. And see, there's vectors in the fourth quadrant. Okay? And what they want is the speed, meaning the magnitude of that vector. Okay? So the speed is equal to 6.64 square plus minus 4.41 square. Okay, so that's the speed with which it hits the floor. All right. Again, let me review a couple of things, just physically. All right, so this is a parabolic trajectory. Okay. There's the acceleration. You want to draw an x and y axis. The y component of the motion gives you the time of flight. Okay. The higher you fall from, the longer you are in flight. Okay. And the further you fall, the greater your x component of velocity. Okay. You guys understand? Any questions on that? All right, so here's a similar problem, except that now we're dropping this from a much higher height and shooting it with a much greater velocity. Okay, so an airplane flying horizontally with a speed of 500 kilometers per hour at a height of 800 meters drops a crate of supplies. If the parachute fails to open, how far in front of the release point does the crate hit the ground? So you release it there, and you want to find this distance. Okay. In the previous problem, they gave you the distance and they wanted you to find the speed. In this problem, they're doing the opposite. They're giving you the speed at which it was released, and they want you to find the distance. Okay. So it's essentially the same problem. Instead of one variable, they're asking you to find the other variable. Okay. Again, we'll set up the problem. Here are the axes. Okay. And you want to write down V naught and A. Here's your acceleration vector, and there is your V naught vector. But let's calculate 500 kilometers per hour equal to 500. A kilometer, that's 10 to the power of 3. That's that many meters. And 1 hour is 3,600 seconds. Okay. So I'm converting that to meters per second. Okay. And you can see that this is just taking this number and dividing it by 3.6. All right, so here's my V naught, 138.9 I plus 0J meters per second. Help me out with the acceleration. Okay. All right, so now we're all set. So let's look at the Y motion first, and we'll get the time of flight. Okay, so Y minus Y naught equal to V naught Y T plus 1/2 AY T square. Final Y position is 0, initial Y position is 800 meters. This is 0 minus 1/2 times 9.8 T squared. Okay. So T is 800 divided by 4.9 square root of that. Okay, this object was dropped from quite a height, and it was in flight for 12.8 seconds. Okay. 800 meters is, you guys see the Riddle plane flying along the beach? That's about 800 meters. All right, now that we have that, let's look at the x motion. X minus x naught equal to v naught xt plus 1/2 ax t squared. Ax is 0. This is 0. We'll want to find the final x location. The speed is 138.9 meters per second, and the time of flight is 12.8 seconds. Okay, so it falls 1,700 meters away, 1,800 meters away. 1,600 meters is a mile, so a little over a mile. So if you drop the plane so if you drop this here, a mile is from here to Bethune-Cookman College. Well, maybe a little less than that. Yep.
Why on the velocity, or sorry, the acceleration vector, why is the first component 0?
So there's the acceleration vector, there's the x-axis, there's the y-axis. If you draw a vector this vector has no x component.
Right. So if it was like pushed, like if the box was pushed in a horizontal direction and then you have an acceleration.
Okay, so if you draw your axis like this vector A as 0 I minus gj. Did you understand that?
Yeah.
Okay, so this is the language you choose to speak in. This is what you're trying to say. Okay, so the direction, magnitude and direction of this vector doesn't change. In this language, that's how you say this. In this language, this is how you say this. You're saying the same thing. Yeah. If you want to make life hard for yourself, choose an axis like this. And then A will have a x component and a y component. Okay? Okay, I urge you guys to go home and practice the problems. When I do it on the board, it might appear, you understand it, but once you walk through it, try and go home and work through each step. Okay? And you'll be surprised you'll learn faster that way. Okay. A projectile is launched at an angle of 30 degrees and lands 20 seconds later at the same height as it was launched. What is the initial speed of the projectile? What is the maximum altitude? What is the range? Calculate the displacement from point of launch to the point to the position on its trajectory at 15 seconds. Okay, so this goes through the projectile motion. Okay, it covers all aspects of projectile motion. So actually, let me so here is the projectile motion. This is the height. This is the range. Okay, again, A is 0I minus GJ. All right, so they tell us a projectile is launched at 30 degrees, lands 20 seconds later at the same height it was launched from. What is the initial speed of the projectile? They want you to find that, okay? Now let's write down the initial velocity. Initial velocity is initial speed cosine 30I plus initial speed sine 30J. Okay. And we have the acceleration vector. Acceleration is 0I minus GJ. All right, so in this problem, we know the time of flight, we know the initial position, and we know the final position. Let's look at the y motion first. Y minus y naught equal to v naught y t plus 1/2 ay t squared. The final y position is 0, initial y position is 0. So this is 0 equal to v naught sine 30 times 20 seconds minus 1/2 9.8 20 squared. So you see from the y motion, we are able to calculate the speed. That's the only unknown. Okay. So let's do that. So 0 equal to 10 minus 4. Okay, the object was in flight for 20 seconds. That's a long time. And so its launch speed has to be quite high. It's 196 meters per second, 200 meters per second, 200 meters per second. Remember, 10 meters per second is about 10 miles and 25 miles an hour. So 250, 500 miles an hour, roughly. Okay. All right, what is the initial speed of the projectile? We found that. What is the maximum altitude? What is the maximum altitude? Okay, we've sort of stated this. When does it reach the maximum altitude? I'm sorry? When the y component of the velocity is 0. It'll have a horizontal component. also you can tell from here, it'll reach the maximum height at 10 seconds. Okay, so we can go back here. We'll put that as the maximum height, h, and put 10 seconds. Okay. So, well, there's also this formula for the height. You can check V naught sine theta squared divided by 2g. That's the formula that's given, but I like to solve it from first principles. We'll solve it like this. Okay, so this is the final position h. This was the initial position, which was 0. H equal to V naught is 196 sine 30 in 10 seconds minus 1/2 9.8 meters per second square 10 seconds square. No? So it reaches a height of 490 meters. And you can check that from here. And that should also work out the same. Okay. Okay, so you can use the maximum height formula, but so this is easy to remember because you use it often enough. And okay, so what is the maximum height? What is the range? The range is the x component of the motion, x minus x naught, to v naught xt plus 1/2 axt squared. This is 0, x naught is 0. So the range is 196 cosine 30 times t, which is 20 seconds. Okay. And you also have the range formula. You can solve it using this v naught sine 2 theta. Okay, I don't remember the range formula. You can look it up in the notes. All right, so here is the range formula. Here's the x distance travel in 20 seconds. So 3,395 meters. Okay, so that's about 2 miles. A little over 2 miles. Calculate the displacement from the point of launch. So now part D, they ask you calculate the displacement from the point of launch to the position on its trajectory at 15 seconds. So there it was at 20 seconds. There it is in 10 seconds. So it's somewhere here in 15 seconds. Okay. So what you want to calculate is its x coordinate and its y coordinate at 15 seconds. Okay. So x minus x naught equal to Okay, so its position at 15 seconds is 2546I plus 368J. Okay, that's the position. You guys following this? Okay, so here is a similar problem, except that there's a slight complication. Okay, so they give you the launch speed, they give you the launch angle, and they give you the spot where it will launch. It'll land. So a projectile is shot at a hill, the base of which is 300 meters away. It's shot at 60 degrees with the launch speed of 75 meters per second. The hill can be approximated by a plane sloped at 20 degrees relative to the coordinate system shown. The equation of this straight line is, see, tan 20 is the slope of that line. Okay, so they have given you this straight line, the equation to the straight line in the slope intercept form. Y equal to mx plus b. The y-intercept is minus 109 meters. Where on the hill does the projectile land? Okay, so they're asking you for the x and y coordinate of this point. Okay. Did you guys understand that? All right, so let's look at the x motion, x minus x naught Okay, this is 0, x, this is 0, equal to 75 cosine 60 t. So they want us to find the x and y coordinate of this. They want us to let us know this. But it seems like we have 2 equations and 3 unknowns. We don't know t. So we seem to have a problem. Where is the missing piece of information? Here is the missing piece of information. They tell you it lands on this hill, and on the hill, the x and y coordinate are related like that. Okay, so y is equal to tan 20. Tan 20 is 0.36, so 0.36x minus 109. There's the third equation. Okay, so what is it that we are interested in? We're interested in the x and y coordinate. So what we can do is we can, for y, we'll substitute that equation. For x, we'll put that in there, solve for t, and then come back and solve for x and y. All right. So what we're going to do is put 1 and 2 into 3. All right, I'm going to do it right here. So y is 65t minus 4.9 t squared equal to 0.36. X is 37.5 t minus 109. So you guys see this by putting the information from 1 and 2 into 3. Now we have a one variable equation. And we can solve this. Okay? All right, so let me grab this. Negative solution is the following. So this is 0 seconds. This is 12.3 seconds. If you extend this, it had negative 1.8 seconds. So if you had extended this hill, if you launch from there, that would have been minus 1.8 seconds. That would have been 0 seconds. That's 12.3 seconds. Okay, that's what that solution is. So that's on a parabolic trajectory, and it's on the hill at this time and that time. All right, now that we have this time, we can put it in here and calculate the x and y coordinates. So the x coordinate is 37.5 times 12.32 seconds. And the y coordinate is 65t So this is the position of the projectile 12.32 seconds after launch. Okay? And that's the coordinate on the hill. 462I plus 57J meters. So that's where the rock landed. Okay? Okay, that's the coordinate of this point. So here is Venus, the second planet from the sun, going in a circular orbit, and its speed is constant. Is it accelerating? Why? I'm sorry? Direction's changing. And when only the direction changes, which direction is the acceleration? I'm sorry? Perpendicular to the path, and it's towards the center. Okay. And the magnitude of this acceleration is v naught squared divided by the radius of the orbit. Okay. So let's look up Venus's orbital speed. Venus's orbital speed. "35 kilometers per second." Yeah. Venus orbital radius. Venus orbital radius. "108 million kilometers." Okay. Our orbital radius is 150 million kilometers. Okay. So the acceleration is 35 kilometers per second, so 35 times 10 to the 3 meters per second square, 1.08 into 10 to the 11 meters. Okay, so this will work out to, that's 10 to the power 6. Well, we'll make it 3.5 times 10 to the power 4, 10 to the power 8, and this is 10 to the power 11. So it's 10 to the minus 3 meters per second square, and that's 3.5 squared divided by 1.08. Okay, so the acceleration is, this is roughly g, 1,000th of a g. Okay, so per pound, the force that the sun exerts on Venus is 1,000th of the force that the Earth exerts on something on its surface. Okay. All right, so this is addition of velocities, and pilots do this all the time. So a small plane flies at 200 kilometers per hour in still air, okay? If the wind blows directly out of the west at 50 kilometers per hour, see, the wind speed is comparable to the speed of the plane. So you can't ignore that. Okay. In what direction must the pilot head her plane to move directly north across the land? Okay, so you got to fly west. So this is the velocity of the plane with respect to air, and then air with respect to ground. That gives you the velocity of the plane with respect to ground. Okay. So again, the rules are velocity of the plane with respect to ground, which is what you want. So if you want to head in the northerly direction or whatever, you know your destination, and so that's what you want. And you fly your velocity with respect to air plus the velocity of air with respect to ground. Okay, so all we did was we inserted this letter between the two. Okay, so that's how you remember it. All right, so what you want is, so let's say this angle is theta, and that's what you want to try and find. Okay, so velocity of the plane with respect to air equal to, this is 200 kilometers per hour. This is 50 kilometers per hour. Is the x component is minus, so we're going to write it in, so the x component of this is that, which is 200 sine minus 200 sine theta I plus 200 cosine theta j. Velocity of the air with respect to ground is 50 I plus 0 j. And so what you want is, for the x component of the velocity of the plane with respect to ground, you need that to be 0. Okay, so 0 should equal x component of this plus the x component of that. 0 equal to this plus that. So the pilot needs to fly 14.5 degrees west of north. So here's another problem. A river is moving east at 4 meters per second. A boat starts from the dock heading 30 degrees north of west at 7 meters per second. So here's the river moving at 4 meters per second, and a boat heads 7 meters per second, 30 degrees north of west. The river is 1,800 meters wide. That's a little over a mile. What is the velocity of the boat with respect to Earth? And how long does it take the boat? Okay, so a velocity of boat with respect to Earth is equal to velocity of boat with respect to water plus velocity of water with respect to Earth. Okay. Here's the velocity of the boat with respect to water, and then we'll add the velocity of water with respect to Earth. So velocity of boat with respect to water is, there's the x component and there's the y component. Minus 7 cosine 30 I plus 7 sine 30 j. Okay. And the velocity of water with respect to Earth is that 4I. Again, in this thing here is the axes. All right, so the velocity of the boat with respect to Earth is the sum of these two vectors. So it's minus 6.06I plus 3.5J plus 4I plus 0J. Meters per second. Okay, so the net velocities, so this vector plus this vector is a vector something like that. Okay, so there's the x component of the velocity, there's the y component. Okay, so when the boat starts, so it'll end up somewhere there. Okay. What we want to find is how long does it take to cross the river. Okay. Now, so this is not the to cross the river. Well, you're starting here and you end up somewhere there. If you want to cross the river the fastest, okay, you want to make this 0, so you would have had to point the boat in that a little greater angle. But anyway, okay, so right now you're heading that way. If you headed this way, then you would have crossed the river the fastest. Yeah. But anyway, let's look at the y motion. Y motion, y minus y naught equal to v naught y t plus a y t squared. Okay, 1/2 a y t squared. You don't have any acceleration. Okay, so this is 1800 meters, and v naught y equal to 3.5 t. So t is so you're traveling 1800 meters, and the y component of the velocity is 3.5 meters per second. It takes you 514 seconds, or roughly 9 minutes, to cross the river. Okay. Okay. This problem says a geosynchronous satellite orbits Earth at a distance of 42,000 kilometers and has a period of 1 day. What is the centripetal acceleration of the satellite? Okay, at a distance of, and that's the distance from the center of the Earth. So I guess they should have been. What is a geosynchronous satellite? Anybody? Okay, so a geosynchronous satellite is a satellite that is on the same spot in the sky at all times. Why is that useful? So, if it's on the same spot in the sky, I can bounce a TV signal off of it. Okay? And then I can charge you money for satellite TV. Okay? Well, so that's how when you watch soccer that's happening in Europe, they're bouncing off that signal off that satellite, comes to your local station, and then they send it to you via cable. Okay. Now, here's the deal. So, a geosynchronous satellite, it takes 1 day to go around the Earth. Okay. Now, it turns out that, so let's say this is Earth, there is its axis of rotation, and there is the equator. Okay. So, if you're a satellite, and if your the radius of the orbit is 42,250 kilometers, okay, you'll go in a circle, you're in a circular orbit, and it takes you 24 hours to go around. But if you're in an orbit like this, you won't stay on the same spot about the Earth. The Earth is turning and you're going around like that, you won't be on the same spot. The only orbit that'll make you be on the same spot is the orbit has to be right above the equator. And you have to be going in the same direction as the Earth. If you go in the opposite direction, it'll take you one day again, but again, you're not on the same spot above the Earth. So a geosynchronous satellite is directly above the equator at a distance of 42,250 kilometers. Okay? In fact, those are the most expensive parking slots. Okay? So there you go. So you see, those slots are allocated to countries. There's one at every half degree. So there's 720 slots. Okay. Well, you can see there are several satellites parked on that same spot. How does that work? You communicate at different frequencies. One is talking on green light, the other is talking in red light, and so on. Okay. So this is all right. So now you know about geosynchronous satellites. What is the centripetal acceleration? So you're going in a circle. The radius of the orbit is there's the centripetal acceleration is v squared by r. What is the speed v? The speed v is 2 pi r over the period of the satellite. Okay, so 2 pi r over the period of the satellite. What is the period of the satellite? 1 day. Okay. So now we can put in these guys. So the centripetal acceleration and 1 day is 24 hours into that's that many seconds. So that far above the surface of the Earth, the acceleration due to gravity is only 0.22 meters per second squared. Okay. All right, guys. So we'll end that